All right, welcome to another pre-recorded lesson. Today we're going to finish off Unit 1 and we're going to start Unit 2. And so on page 25, you're going to see that at the very end of the dimensional analysis section, we're going to be dealing with area and volume. So we're going to be converting units that involve squared units or cubic units, which works exactly the same as regular conversions, except sometimes we need to square our numbers. So let me show you what I mean. In this first question, it says convert 600 or change 600,000 centimeters squared to square meters. So what we started with is 600,000 centimeters squared, and we want square meters, which is meters with a square on top. This is the big difference. We're going to be ending up with squared units, and we actually started with square units. The setup is exactly the same. We still need to say, okay, we need to cancel centimeters and we want meters on top. But the difference is that there's going to be this square. So we actually have squareds to think about. And use the same conversion. There are 100 centimeters in a meter, so you still put 100 there and put a 1 on top. But because everything's squared, remember that we need to put squared on these and you'll be fine. All right, you don't really need to put the square on the 1 because it's not going to change anything. So just remember that if your units are squared, then you square your numbers. And everything else will work out just fine. So that will cancel out your centimeters squared. And then if you take 600,000 and divide it by 100 squared, you end up with 60. So that means that 600,000 centimeters squared is 60 meters squared. Be careful putting that squared into your calculator, okay? Find the button and use it properly. In this case, we have change 575 grams per centimeters cubed. All right, per centimeters cubed, we have centimeters cubed here now, to kilograms per cubic meter. So kilograms per cubic meter, which means meters cubed. These are the units that I want. So similar to the previous question, I'm going to be dealing with actually cubic units in this case. And I want meters cubed on bottom, so I'm going to put centimeters cubed on top. I need meters cubed on bottom. And then use the same conversion. We know there's 100 centimeters in 1 meter, but because we see this 3 here, we need to actually cube the 100 that we have. And that, again, is the only difference. What that will do is it will cancel out our centimeters cubed on top and bottom, leaving us with meters cubed on bottom, which is excellent. And we also need to convert the grams to kilograms. So we already have grams, put it on bottom, put kilograms on top, because that's what we want. If you're losing me here, it's because I'm canceling these grams, leaving kilograms, which is what I want. And then again, think, how many grams are in a kilogram? What's this conversion? And you should know that there's 1,000 grams in 1 kilogram. If you ignore all the color here, all we're doing is multiplying all the things on top by all the things on bottom. So we have 575 times 100 cubed times 1. And then we're going to divide that by 1,000. So we end up getting 575,000. We have kilograms on top, meters cubed on bottom. So you can do, just to be clear here, it's 575 multiplied by 100 cubed. And then all of that is going to be divided by your 1,000, because all the other things are ones. Okay? Hopefully that makes a bit of sense, and that's exactly how we're going to do these problems. If we deal with liters and centimeters, it turns out that there's a direct connection between liters and centimeters cubed. In fact, 1 liter is 1,000 centimeters cubed. Take a look at this table. It says 1 liter is 1,000 centimeters cubed, 1 liter is also 1,000 milliliters, 1,000 milliliters is 1,000 centimeters cubed, and so on. So this is a reference that you should probably remember. Reference this when you need it. Let's see what the problem is. 200,000 centimeters cubed per second. We want to change that to liters per minute. We need liters per minute in the end of this. That's interesting. Let's see how we can do this. Usually the problem starts making sense once you write it down. So centimeters cubed over seconds. What's the first conversion going to be? Let's change our centimeters cubed. We need to cancel that on bottom, and we want to change it to liters. It turns out that's a direct relationship that we can use. they're related here. So let's see, 1,000 centimeters cubed is what 1 liter is. That'll cancel. And now we want to change our seconds on bottom to minutes on bottom. So I put my seconds on top and minutes on bottom. And then how many seconds are in a minute? Well, there's 60 seconds in 1 minute. That's how I do these. So let's double check that our units are going to cancel. Let me get rid of this highlighting. Centimeters cubed cancel with centimeters cubed. Seconds over here cancel with seconds on bottom over here. Nothing else cancels, which means I have liters and minutes left over, which is exactly what I want. Okay, so this is going to be fine. In this case, notice that there's no cube on this, and that's because the conversion is direct. This is the conversion. So be careful, if you're dealing with liter and centimeters, you don't cube the 1,000. It's been done for you. So now we do 200,000 multiplied by 60 divided by 1,000. And what that gives us is, sorry, I'm going to calculate it out, 200,000 times 60 divided by 1,000. You should check this yourself and see if you get 12,000 liters per minute. And I sure hope you do. If you can handle that, then that's the kind of problems you should expect. On the next page, this is just extra practice, okay? And this is going to be left for you. This is extra practice. I'm only going to go over this if you ask me to do so. But what I'm going to do is put down all the answers here, okay? So you can pause the video and try this to your heart's content, and I'll put the answers here and slowly scroll through them. And here we go. This is all the answers in one place. You can pause it here if you want to compare. And zoomed in, these are the final answers. We'll slowly move through so you can see them. Pause at any time to check. If you have trouble getting any of these answers, please jot them down. Let me know what the questions are and I'll go through them with you, okay? But for now, these are just the final answers that you can practice with. Notice that these questions, these conversion questions, were not included in your assignment, 1 or 2. And so it's very important that you try these practice questions. If you can get this, then anything that I would give you on a test related to this, you'd be able to handle. That's the end of Unit 1. I'm going to jump right into Unit 2 right now. Okay, welcome to Unit 2. And Unit 2 is all about triangles. In fact, the next couple of units are going to be all about triangles. And this is going to be starting with the 6 trigonometric functions. You might recognize those as sine, cosine, and tan, and then they have their related functions, cosecant, secant, and cotan. You don't need to know what those mean yet, but maybe you recognize them, okay? Actually, I'll keep those there. So the first thing we're going to do is just some basic housekeeping, trying to remind you what you need to think about when you're dealing with triangles. And we're going to start that by defining the important pieces of a triangle. And we start by defining a ray. So a ray is just a line which begins at some point, but it has no end. A ray is named by its beginning point and any other point on the line. So you can see in this diagram, it has some points starting at A, and then it continues out on forever. In fact, it could go on forever. There's no set size of this line, but another point on the line here is B. And so again, it can go on forever, but it's saying that it's crossing through the point B, which is why the ray is called the ray AB. Angles are when we have 2 rays, sorry about that. Angles are when we have 2 rays with a common beginning point, which would be a vertex. So in this case, the vertex would be B, for example. This like corner piece here, sorry, it's very loud out here. Very loud light going by the house. An angle is formed by rotating the terminal ray about the vertex from the initial ray. So what that really means in English is that we might start with this initial line here. Here we have this initial ray, C, and then we've brought a second ray up. We've kind of rotated it through and moved it up. We have a second ray now, and that's called the terminal ray. And it creates an angle. We've swept out an angle. So if you were to look at this angle here, for example, this is a ray that already exists, and we'll sweep out an angle. That arm here, the pointed one over here, would be called the terminal ray, and the initial arm over here, that would be the initial ray. So the angle between them is the angle that we're talking about. All right, and one more thing to talk about is it says when naming angles, the middle letter always denotes the vertex. So in this case, the middle angle is being denoted by B. It's saying ABC, the angle in the middle, is the one that has the angle that we're talking about. If it was DEF, maybe we have an angle that looks like this. One of these would have to be D, one of them would have to be F, but the important thing is that E is the one in the middle, okay? So that's something to keep in mind and remember. Maybe I'll make it more obvious by making it more pretty color. Okay? It says here in trigonometry, Greek letters are often used to name angles. And so if we look in, it's very, very hard to read, but alpha is actually the angle. Alpha looks like that. That's this one. Beta looks sort of like this. And then we have theta, a very common one, is that angle in here. And we can use either of them. It doesn't matter. For example, if we have a problem where there's more than one angle, sometimes we'll call one theta, and then because we've already used the angle theta, or the symbol theta, we'll move on and call another one alpha or beta. But that's the big idea. You can use it whichever one you want, depending on the situation. So the next section says an angle formed by a complete rotation of the terminal ray about the vertex measures 360. And what that means is if we start on this initial ray, and we are to rotate a terminal ray 360 degrees, well, you just get back to the start. So what it means is that 0 degrees is the same as a 360 degree turn, which is the same as the 720 degree turn, and you continue this process by adding 360 each time. Okay? They're all the same. So looking at it from another perspective, if we just look at this angle here in the middle, ignore all the other stuff, the angle is getting bigger, 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 bigger. This would be 180 here. We get to 270, and then look, this is 360. That's what it means. And when we get back to the start, it starts over because it's the exact same. 0 is 360. It means the same thing. So nothing to get too excited over there. Complementary angles and supplementary angles are quite interesting. They're very similar, but easy to get confused. Complementary angles are two angles whose sum is 90 degrees. Supplementary angles are two angles whose sum is 80 degrees. So let's take another look at a little applet here. So this is a complementary angle situation. Look here, we have an angle that's cut down the middle. Look at the red side of the left side, DCE. That angle's 34. Its complementary angle is currently 56. If you add 34 plus 56, it equals 90. And that's because we see a 90-degree angle. And no matter what way I do this, look, if I make the red angle smaller, make it 10, the other one's going to be 80 because the other angle is its complement. If we go all the way up, make it bigger, for example, one of them is 70, the other one has to be 20 because they both have to add up to 90. So that's complementary angles. Supplementary angles, if you just bear with me, add up to 180. So no matter what, let's just make this one, for example, 45. Think about what do you need to add to 45 to make 180, or a full half turn, and 45 plus 135. So we see this angle over here, 45 plus 135 must add up to 180. If we move this around, change them up, they always together, once you add them up, no matter what I do, they'll add up to 180. And that is the definition of a supplementary angle. So let's see what this means. If an angle measures 65, what is the measure of its complement? So once again, complement means they add to 90 degrees. And so if an angle measures 65, we know that 65 minus something, or plus something. So really we can just take away from 90. So 90 minus 65 is going to be its complement because we know they add to 90. So take away from 90 and we'll figure this out. That's 25 degrees. Just to prove that, you have 65 plus some mysterious amount is going to be 90 because of the complement situation. That means that mysterious amount must be 90 minus 65. So this idea checks out for complements. If an angle measures, this is the next question now, if an angle measures 34 degrees, what is the measure of its supplement? And let's remember that supplement means we add to 180 degrees. And so in the same situation, we'll just start with the 180. That's the total we need to make. We take away 34 and we'll figure out what the supplement is. And 180 minus 34 is 146 degrees. Some students find it difficult to remember which one's which. And so I always remember that the complement goes with 90 degrees, the supplement goes with 180, and the reason I can remember that is kind of a silly way. C comes before S in the alphabet. So in the same way that C comes before S in the alphabet, 90 comes before 180 in terms of numerical order. So just one silly way to remember it. If you're always mixing up which one's complement, which one's supplement, remember the alphabet. C comes before S. So let's take a look at number 3. Based on the diagram below, what is the complement of LKM and what is the supplement of PKO? So let's look for LKM. LKM is LKM. And remember that complement means we need to add to 90. So we just look for its complement here. In this case, it's going to be this one here, because they both need to add up to this 90-degree angle, this right angle here. So the angle is MKN. We can call it MKN, or we can call it NKM. It doesn't matter the order. The important thing is that K is in the middle. Because K, I'm going to say, remember, K is the vertex. Vertex means that corner of the angle. The next question was the supplement of PKO. Once again, I'm going to look for PKO. 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 I'm going to make this red. The supplement must be the other end of it making 180 in total. So it needs to make this full turn. Well, what am I missing? I've got PKO. I must make this angle. And this angle is going to be, it looks like OKN or NKO. Again, the order doesn't really matter. The vertex is what matters. And then these, in fact, have the same vertex. So just as a reminder here, supplement means add to 180. And this is how we do these questions. If you're thinking complement, think 90. If you're thinking supplement, think 180. And you shouldn't have much trouble. So we're going to move on here and continue our exploration, I guess, into the definitions here. Can't really do much unless we know what all these terms mean. So let me take them one step at a time. We're going to classify angles as right, acute, obtuse, or straight. So we'll start with straight because it's an easy one. It's an angle formed by rotating the terminal ray through 1/2 of a complete rotation. So what this means is that we actually have the initial ray here, and we have another ray which would have started on the terminal ray and then moved all the way around. And now we actually have two pieces. That's a straight angle. So if anyone who's done, woodworking and things like that, like a straight edge, straight angle, it just means a straight line. It's a 180. So that's a pretty straightforward one. The next one we'll call a right angle, which you've probably seen before. A right angle is this idea that we have a perfect 90-degree corner. So it's an angle formed by rotating the terminal ray through 1/4 of a complete rotation. So the terminal ray here we'll just color in blue. And then if we were to pull it up and end up with a second ray straight up from it, perpendicular, it would be 90 degrees. So right angle, you'll see a lot of times being called perpendicular as well. And they both mean 90 degrees. All right? Oblique angle means an angle that's not right and not straight. So oblique, any angle that is neither right nor straight. So it's not 90 degrees. I should probably split this up. Neither right nor straight. So it's not 90, and it's not 180. So anything in between. So 45 degrees, literally anything that's not 90 or 180 is called oblique. It just kind of means weird angle, not perfect. Acute angle is an angle that's between 0 and 90. So for example, 30 degrees, I'm just putting some common ones, 45 degrees, 60 degrees. These are all acute. it just needs to be less than 90. And you'll see that it's this small angle. It's actually, I like to think of it as like, it's actually a little tiny cute angle, like not a big fat angle, a little cute one. Because anything below this 90-degree mark, or what would be a right angle, would be considered acute. On the other side of that, obtuse is something that is between 90 and 180, bigger than 90 and smaller than 180. And you can see that we're comparing it in this case to the straight angle, not the right angle. So examples of that, common ones, are like 135, 160, things like that. You can even add in 115 maybe. So 115 is a pretty common one. Literally anything between 90 and 180 will do. Just put the little degree symbol on there. All right, and I've put a little comic here just as a slight reminder. Little silly comic, right angle. I'm always right, looking all cocky. Acute angle, but I'm cuter. So I'm small, but I'm cuter. Acute. Acute angle means small. Anyway, I've probably over-explained that one within an inch of its life. Oh, so let's move on to something a little different, actually building these rays into triangles. So the first thing we should do is define a triangle, and you probably already know what this is. It's three straight lines all attached together. But the most important thing here is that we actually mention this A, B, and C. They're capital letters. The capital letters are what we use for the vertices. So it says right here, capital letters are used for the vertices, which are the corners, this, this, and this. And lowercase letters are used for the corresponding opposite sides. So by opposite, what that means is that if we take our letter A and we go across the triangle, we will find its corresponding side. So always think going across the triangle to find its corresponding letter. Okay? Capital for the vertices, lowercase letters for the sides. Scalene is a name for a special type of triangle which has no sides equal. So be careful to look at this. This is one dashed line, this is two dashed lines, and this is three dashed lines. The dashed lines denote if the sides are equal or not. For example, if we look ahead to the equilateral, these all have a single dashed line, which means all same length and all equal angle. So scalene, no equal sides, no equal angles. All the angles are different, all the sides are different lengths. Equilateral means equal, three equal sides, three equal angles. And we'll notice here, this is summarized in this little table here, or in this little note. Angle A is equal to angle B is equal to angle C, and all the sides A, B, and C are the same. So it sometimes helps to write down some letters, A, B, C, capital. Notice what I did, and then you can pause the video and say, where would little a go? Where would little b go? And where would little c go? Because those are the lengths of the sides. And if you've taken time to think about that, it's always opposite of the angle. So a would be here, b would be here, and little c would be there. And remember, it goes across from where they start, across from their accompanying vertex, we should say. And then this 60-degree thing is pretty important. I'm going to write down equilateral triangles. Equilateral triangles always have interior angles, which means the angles on the inside. Interior angles of 60 degrees. Okay, that's because all the angles in the triangle add up to 180, and if you divide it by 3, because you have 3 angles here, gives 60. So 60 plus 60 plus 60 equals 180. That's why we get this 60 here. We'll see more about that later. Isosceles triangles. Isosceles is 2 equal sides and 2 equal angles. So remember what I said before. We have our dashed line. We have 2 sides here which have the same symbol, the same single dashed line, which means they're the same length. And it's trying to tell us something over here. Let's look and see what it is. It says angle D is equal to angle F. That's what this little symbol here for the angle means. And then it's telling us that side D equals side F. Remember, D is across from the large capital D, and lowercase f is across from the F. So hopefully you can see what this means. It means that the lengths are the same and the angles are the same. Soon we'll do examples with this, but for now it's all set up. So I know it's a little bit dry, but take time to make sure you understand what I'm trying to say. Finally, and this is the last type of triangle we're going to talk about, is a right angle triangle, which means we have a single right angle. It's going to be right here. And a right angle, which I've said before, is 90 degrees. Okay? Equilateral is dealing with 60-degree angles. Right angle has one angle of 90 degrees. And it gives that little right angle symbol. So it says, might as well make that kind of pretty there. The side opposite the right angle is called the hypotenuse. This is extremely important. I don't think there's many other ideas in trigonometry that are more important. So the side opposite the right angle. So we find the right angle. Okay, it's right there. Find that. The side across the triangle is the hypotenuse. The longest side, always, for a right angle. The other two sides are called legs. So B is one of the legs, A is one of the legs. And the reason it's called legs is you can think of C being kind of our most important angle. C is most important because it gives us our hypotenuse, and then the leg comes out from that corner. I don't know if that's like the official reason why we call it legs, but that's the way that I think about this. Of course, we can draw the hypotenuse in blue here. So it's always the case. So I could give you any old triangle. Let's just say I give you this, right angle. You should be able to tell me right away that this is the hypotenuse. And you should know that because you look at this right angle and you're like, well, it's across from that. It must be the longest side. And that's going to be extremely important later. Let's get a couple more definitions out of the way. The angle sum principle. The angle sum principle states that the sum of the three angles of any triangle is 180. I actually already talked about this. It means that in any triangle, doesn't matter what triangle it is, literally makes no difference what the triangle is. The angles, the three angles that we have, are going to add to 180. So very important piece of information here. Given any two angles, we can find the measure of a third using this principle. Let me show you a little proof that the angles inside a triangle do indeed add to a straight angle, 180. Okay, we have this triangle. It could have been any triangle, right? It doesn't matter. It could look like this. It could look like this. Who cares? It doesn't matter. What matters is that if we were to look at all three of these corner angles, if we were to add them all together, we should get 180, right? But we don't need numbers to prove that. Let's just take those and see what happens. Bam. It makes a full straight angle, 180 degrees. Let's make a new triangle. Let's make it really squishy. You can be like, well, sir, I don't think this is going to be 180. Well, whoa. It is indeed 180. You cannot make a triangle that doesn't follow this rule. It's just not going to happen. It's the rules of math. So we try one more time. Boom, 180. And you can actually do this yourself at home, not even with a computer. You can draw a triangle on paper. You can cut it out and then snip all the angles off, try to line them up. You will absolutely get a flat 180 degrees. So something to try, but if you don't believe me, or if you're too lazy to try that, believe me, they always add up to 180. So let's go just a little bit further and do our last theorem of the day, which is going to be the Pythagorean Theorem, which I believe you would have seen before, and hopefully you have, but if not, this is going to be a nice review for you. So the Pythagorean Theorem, we're going to use it to calculate the unknown length of a side in a right triangle. We usually use it when we know two of the side lengths and we want to find a third. want to find a third side length. So let's be super clear here. It says in any right triangle. Okay, let's not go anywhere else. It must be a right triangle. You cannot use Pythagorean Theorem unless you have a right triangle. If it's any other angle, if you don't see a right angle somewhere, you are not allowed to use Pythagoras, okay? Rewind this video if you need to listen to me say that again. It's so important. It must be a right angle. But as long as we have a right angle, it works really well. So in any right angle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the two legs. What it really means, I mean, if we don't want to be talking through the specific math terms, it means that the hypotenuse squared, so let's just look at the right angle and go across, that's the hypotenuse. So we have the hypotenuse here. If we know that length, then the square of that length must be equal to the length of the first leg, in this case A, it doesn't matter which one's which, just the two legs, right? One leg and then the square of the second leg. So as long as we know two pieces, we can find the third. For example, if we know A and B, we can solve for C. Or if maybe we know C, maybe we know the hypotenuse in one of the legs, but we're looking for B. We can do this. As long as we have two knowns, we can solve for the third. Now, before I move any further, I just want to show you one more visual proof that this law, this very, 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 very important law, actually works every single time. So I've set up a basic triangle here. It's called a special triangle because the sides have a nice simple whole number pattern, 3, 4, and 5, and the numbers that we're working with end up being simple. So just bear with me here. Let's just say we have this side here, or let's start with this one. So we have 3 squared equals 9. Okay, and that's represented by this big grid here. Okay, 9. The 4, if we square that, 4 squared, that gives 16. And that's represented by these 16 blocks here. The third side, Pythagoras would state that the third side here, 5 squared, 25, needs to be equal to the sum of the other sides. So what it's saying is that, 3 squared plus 4 squared equals 5 squared. That's what Pythagoras is trying to tell us. And it turns out that he's right, because 9 plus 16 is indeed 25, so that does check out. But we can see it visually too. If we see all of these blocks here, we've got 9 blocks from the 3, and we've got 16 blocks from the 4. Look at how this works. We can add all the ones from the 3, 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks, and then add our 16 blocks, we get our 25 blocks in total, which you can see yourself, hopefully. So I'll erase it so you can take a look at this if you're interested and count it yourself. We can see that for sure the hypotenuse squared is equal to both of the sides squared. And this you might think this is just some special case for this particular triangle, but actually it works for any triangle. This rule always holds up. So hopefully that was something interesting to you. And if not, it's not the end of the world if you don't fully understand it. Let's try an example, and then we'll try 2 examples, and then we'll be done. So example, triangle ABC has angle B of 90, A of 12, and C of 15. So you're going to want to draw the triangle, because otherwise you're going to be trying to feel around the dark. So just make a right angle triangle. I should probably mention that. Draw a right triangle, which means it has an angle of 90 degrees. And the angle of 90 degrees here is our B. So I'm going to say that's our angle of 90 degrees, and I also know that that means that my hypotenuse is over there as B. As for A and C, it doesn't matter. Just put your vertices anywhere. I like to just put A, B, C like this. And then we know we have A here, and we have C here, because of the reasons as before, right? The hypotenuse is always across, and the sides are across from the accompanying vertices. So we know A is 12, probably put that down. C is 15. And let's see what we got. We're trying to find B. So we know that C squared equals A squared plus B squared. And let's take a look and see what we have been given. Well, in this case, it's very tricky what they do here, because this is the formula, but they used A, B, and C. So I'm going to say it can be misleading. What I'm trying to say here is they used A, B, and C, but they used them in a different order. In this case, C and A are our legs, but in the formula, this is the hypotenuse. So I'm not even going to put that there. In fact, I'm going to keep it there, but I'm going to cross it out. It's a little bit confusing. Let's write down that the hypotenuse squared is equal to one of the legs plus another one of the legs. Just for now, just to remind you that this is what's really happening. And now we can fill things in. We do not have the hypotenuse, but we have both legs. So just fill in the information. Hypotenuse, which in this case is b squared, equals leg 1. Let's just call it a. So a squared. And then the second one, let's call it c. The order doesn't really matter. I just put it in alphabetical order. And now one step further, let's fill it in. A squared is 12. C squared, 15. All right, now we can fill out that right side. We're just doing bed math, so I'm going to do the exponents. 12 squared is 144 plus 15 squared. So all things considered, it's 369. And then we have one thing left to do. We need to divide both sides, square root both sides. And what this looks like is we square root that side. It'll cancel the square, which means b is the square root of 369. So b equals the square root of 369, which is 19.2. And I'm just going to keep it at one decimal place. If you calculate that, the decimal actually goes on forever, but this is perfectly fine. We can leave it as 19.2. So the only other thing I would add here is that some students like to leave it as the square root version, 3 square root of 41, which is technically the full exact answer. That's okay, you can leave the decimals, and usually we round to one decimal place. Let's move on to the final example of this video. Example, triangle PQR has the angle P of 90 degrees, P equals 32, and R equals 28.3. It says to find Q. So it's extremely important that we draw the triangle first, because that will give us focus as to what to do next. So I'm just going to split things up, or shake things up a little bit, and draw the triangle this way, because we could be given a triangle in any orientation, really. I'm going to put my right angle down here. And remember, it says that the angle P here is 90. Okay, so that will be, I'll put that down here, P, that's our 90-degree angle. And then we have draw the triangle PQR. So we'll start here at P. Let's just go this way to draw or write our letters. So P, Q, R. There's nothing wrong with having drawn, if you were to draw the triangle PQR like this, it really wouldn't make a difference because this isn't to scale or anything. We're just sketching it. The important thing is that we've put down all of our data. So the angle P is 90 degrees. We actually know the size of side P, which is across from it. It must be the hypotenuse. So P is 32.0. Turns out we're given the hypotenuse length this time, which is great. And then R, little r, is going to be 28.3. So we'll go across from big R to find little r and say R is 28.3. I'm going to write out the formula this time, because the first time around I wanted to be clear with what we were talking about, but maybe this time around we can make more sense of it. So I'll write below it, this is the hypotenuse, this is a leg, and this is another leg. So let's write down what we know. Our hypotenuse in this case is P. So I'll write it out in our letters. P squared equals one of the legs, doesn't matter which one comes first. PQR, maybe? Yeah, let's just go in alphabetical order. So PQR. So really, this is what we have. I haven't changed the formula. I just wrote it out in the letters that we had. And let's see what we have. We have P. We do not know Q. We're being asked to find Q. Find Q, so we don't know it. And we definitely have R. So we're going to fill it in, and then we'll just solve for the unknown. P squared, so this is 32.0 squared equals Q squared plus 28.3 squared. And really we don't need those brackets there, but I was a little bit nervous just in case we're going to have negatives, but I don't want to confuse you too much, so maybe let's keep those brackets out just to clean it up a bit. I'm going to bring my number over here, and I'm going to multiply both. I'm going to square both. So 32 squared is 1024. I'm going to bring 28.3 squared over. 28.3 squared is 800.89. And that equals Q squared. So I'm going to simplify the left side. If I do that, I end up with 223.11 equals Q squared. And hopefully you remember what I did last time I had it squared. I square rooted both sides. So I'm going to go ahead and do that now. That cancels the square. Square root's the left side. I'm going to say Q must equal whatever that answer is. And in this case, my answer must be 14.9. And that's our answer. As a final check, I can square the legs and see if they add up to the hypotenuse. So 14.9 squared plus 28.4 squared should equal 32. Let's see if it does. 14.9 squared plus 28.3 squared equals, oh, that should be squared. 1022.9, square root it. Actually, I'll write all this out for you so you can see it, because I don't want you getting too lost. This is 222.01. The next one, 28.3, square that, we get 800.89. And then if we do 32 squared, sorry, well, 32 squared is supposed to be 1024. Once again, we don't know if they're going to be equal. Let's do the left side and see what it works out to. 222.01 plus 800.89. This gives us 1022.9. So within reason, they're okay, because they're so close. And what happened was I rounded my final answer. And so if I rounded this answer and then used it over here, I'm going to get a slightly different final answer, but that's okay. You just need to be able to have a general idea of whether or not your answer is correct or not. And you don't need to check it. I'm just showing you that you can check it if you want to. Okay? So that's the end of this. I know it's a bit of a long video today, but try to take your time and go through it. It was a lot of time for you to do the examples. So if you want to go back and try the examples yourself, I think that would be a really great idea. From here, we're going to move on to a little more practice in the next class. And if you have any questions, please keep a note of them and send them to me. I'm more than happy to help with anything, but this or the assignments. Have a wonderful day, and I wish you all the best. See you soon.